Alright, so this is going to be acids and bases chapter for us. So the first thing we're going to start with is the properties of acids. So acids will have a sour taste. They can dissolve metals, as you saw in your reactions lab, and they will turn blue litmus paper red. So you can see over here the litmus paper is blue, and then dipping it in the acid will turn it red. It's just like you've heard of the litmus test. It's just the way that we can test an acid or a base. It's kind of old school. Now we have universal indicators and pH strips that turn excuse me, different colors. So an example of an acid would be hydrochloric acid. And we usually like the taste of acids, and so if you're eating something or drinking something that's got a little bit of a sour taste, it's probably acidic. Bases are bitter. They have a slippery feel, so soap is a base. And they turn blue if you have a red litmus paper. So caffeine is an example of a base. Coffee is actually acidic because it has other stuff in it too, but just the molecule caffeine does act as a base. So we have a few different definitions of acids and bases. The first is the Arrhenius definition. So Arrhenius defines an acid as produces hydrogen ions in an aqueous solution, so when it's dissolved in water. So we've talked about this before, the acids that HCl is a covalent compound, but it breaks down into ions, as you can see in this image over here. And then the ions bond with water to form hydronium. So from here on out, every time we see H plus written somewhere, if it's in water, it really means hydronium. And so we can kind of use these interchangeably. A proton, which is H plus, or hydronium, hydrogen ion, we can use these kind of interchangeably because hydrogen ions don't really exist in water. They get taken by the water immediately and turned into hydronium. So Arrhenius also defined bases, and bases are things that produce sodium hydroxide, or sorry, things that produce hydroxide in solution. And so sodium hydroxide is an example of Arrhenius base. So Arrhenius definition has to do with what does it make in the water when it dissolves. So anytime you have an acid and a base come together, Arrhenius, right, we get this net ionic equation. You get the neutralization, meaning it's turning neutral is turning into water. Another definition, and what we usually use in chemistry, is this definition because it talks more about what the acid or base does and less about what it makes. So we talk about acids as proton donors. Remember, a proton is H plus. So hydrogen only has one proton and one electron. You get rid of the electron, it becomes just a single proton. So a base is a proton acceptor. So if you look here at these equations, let's kind of track this hydrogen. This hydrogen here is being donated to the water to make 3 hydrogens here, and the chloride is left alone. And so we can tell that the HCl donated an H, which makes it an acid. We can tell the water accepted a hydrogen, so we can call it a base by this definition. If you're looking here at this other equation, we have a hydrogen being donated by the water to the ammonia, making ammonium and hydroxide where the H used to be. So this is acting as our base, accepting. This is acting as our acid, donating. You'll notice that water can act as an acid or a base. We'll talk about that a little bit later. So we have something called conjugates when you get this definition of back and forth. With acids and bases that are weak, and we'll talk about those a little bit later again, you get a back and forth and an equilibrium. So that means that we can go forward, we can go backwards. So when an acid does its job, what's left over is called the conjugate base. So if you look here, the water was acting as an acid, remember? And so when the acid does its job, it is going to donate a hydrogen and become OH. So this is the conjugate base. So what this can then do is it can go and turn back into water, because this is a reversible reaction. It can turn back into water. When it turns back into water, it's going to accept an H. So it is going to act as a base in the opposite direction. So we call it a conjugate base. Alternatively, if you have a base, like ammonia, its job is to accept, so let it do its job, accept an H, and it will turn into what we call the conjugate acid. So if you look at in the reverse, the conjugate acid in reverse is going to be donating the H. So you can really think about how to identify acids and bases in an equation like this is to look at what they're doing. If it's donating a hydrogen, it's an acid. If it's accepting a hydrogen, it's a base. In the reverse direction, it's the same acid or base, but we call them conjugates. And then you can identify a conjugate acid-base pair by letting that substance do its job. For example, we have water. If it's acting as an acid, we're going to let it do its job, which for an acid is to donate H+. So literally subtract an H, that gives us OH, and subtract a plus, that gives us a negative charge. So this is my conjugate base. Versus my base, NH3. A base's job is to accept H+, so literally add an H+. So we add an H, and we add a positive charge. So this is my conjugate acid. And these are called conjugate acid-base pairs. And here is what I just showed you. Add an H, so let the base do its job, let the acid do its job, and then the other substance that you make is that pair. Here's another example. We can kind of track what's going on here. If this is my acid, I have a hydrogen here. It's being donated. So what's left over is our conjugate base. We can also think about it in reverse. So in reverse, what is happening? The hydrogen sulfate is accepting the H, and so it's acting as a base in reverse, so that's how we can identify conjugate. And again, this base is accepting the H, becoming H3O+. So in reverse, H3O+ will be donating, so we call it the acid. If I put an acid and base together, I get a neutralization reaction. You notice these when you're talking about net ionic reactions with any Arrhenius acid and base. So any acid that has H, any base that has OH. Not all bases have OH though. So if you look back here, notice that we identified ammonia as a base, but it doesn't have an OH. So it's not an Arrhenius base, but it is a Bronsted-Lowry base because of the way it behaves. So you have to be careful with that. A base can be a base without having OH, but an acid has to have H, and it has to be aqueous to be an acid. And so you've done titration math for your titration lab, hopefully, but a titration is just a process where we figure out what an unknown concentration is with a known concentration. And so we can run an acid-base reaction like this, and we can identify what the concentration of the acid is or what the concentration of the base is, depending on which one we know. And so we did this lab where we dropped the base into the acid, and then at the equivalence point, notice that we have exactly the same number of moles of acid and base, and so we're neutral here. And that's when you have that lightest pink. So at the equivalence point, technically it's not pink yet, but one drop over will turn it pink, and so you really want it that lightest pink as you can get it, so where you have your moles of acid equals your moles of base at the equivalence point. So that's what is equivalent at the equivalence point. When this is true, then we can do our math. And so you recorded the amount of base you dropped in, the amount of acid you had, and then you can go from there. So here's some real-life pictures of this. This should be familiar to you. And so let's do some math. So let's do some titration math. So here's a question. Go ahead and pause and work this out, and then unpause and get your solution. So for this question, first I need a chemical reaction. I have two different substances. Anytime you have two different substances and we're talking about converting between the two, you have to have a chemical reaction. So we have hydrochloric acid, we have sodium hydroxide, and if we switch this, it's going to make sodium chloride, which is aqueous always, and water, which is going to be liquid here. And so I'm always going to start with what I know the most about. I want to know the unknown hydrochloric acid solution, and I want to know the concentration. Concentration, I'm going to remind myself, is molarity, which is really moles over liters. So I need moles, I need liters. I have milliliters of HCl, so what I really need here is moles. So I'm going to start with the other substance, the sodium hydroxide. So if I start with the amount of sodium hydroxide, the volume, I can use molarity as a conversion factor. So remember, we're going to take molarity, cross it out, and remember that it's moles per 1 liter. So I need to get to liters first. So I'm going to do milliliters on the bottom, 1 liter on top. And now I can say 1 liter of sodium hydroxide solution is equal to 0.100 moles of sodium hydroxide solution. I get this from the molarity. So this is the molarity. And now I can use a mole ratio. So for every 1 mole of sodium hydroxide, I have 1 mole of hydrochloric acid. I get this from my balance coefficients. And I do some math and I get 0.001254 moles of HCl. I'm not done though because they asked me the concentration, so I need to divide this by the liters. I have 10 milliliters up here. Quick trick, I can just pop this decimal back 3 places, 1, 2, 3, change it into liters, so 0.01000, make sure I keep my sig figs liters, and divide that, and I get 0.1254 molar HCl. For sig figs I want 4, so this will, or 3 actually, so this will work. So 0.125 molar HCl as my answer. So one mistake that a lot of students make when they're doing this is they will use this dilution equation from the last chapter. And I can see how that may seem appropriate because you have a volume, you have a new volume, you have a molarity, and they're asking you for a molarity. So I have M's and V's and 1's and 2's. But for this dilution, I have to make sure that it's the same substance because this dilution does not take a mole ratio into consideration. So I cannot use it here. I cannot use this here because I have 2 different substances. If I have 2 different substances, I must use a mole ratio, and M1V1 does not give me any room for a mole ratio. So just do the stoichiometry out with a mole ratio hanging out here in the middle or in the end. Okay, so moving on, strong acids and strong and weak acids. So strong acids are defined that they have complete ionization, meaning 100% of the acid exists like this. None of it exists like this. As soon as it's dropped into water, it dissociates completely. So you see here all I have is hydronium ions and I have chloride ions. I don't ever have any of this HCl together anymore ever. So a strong acid dissociates completely. So we use this word dissociation, meaning dissolve into ions. 100% dissociation for strong acids. They're so good at being acids, they will never go back. They will never accept a proton. They will only ever donate, and they will donate all of them. So if I make a lot of ions, I'm going to be a strong electrolyte, right? Because electrolytes need to conduct electricity. And so if I get a lot of ions hanging out in solution, I'm going to be a strong electrolyte. So strong acids are strong electrolytes because they create a whole bunch of ions. Here's a list of strong acids. These are 6 strong acids that you need to memorize. Any other acid is weak. So I'm going to help you out with this just a little bit. If you look right here, hydroiodic says, hi, I'm the strongest acid. And so then we can work our way up from here. There's 3 on the periodic table. So iodide, bromide, and chloride are all on the periodic table. So start with high, I'm the strongest acid, work your way up, which means HF, hydrofluoric acid, is not strong. Then you have these other 3, I don't know how you want to memorize this, nitric, perchloric, and sulfuric. They are your other strong acids, meaning that they dissociate 100%. They break apart completely. It doesn't mean that they are more dangerous than any other acid. It just means that when you have this in water, it will break apart completely 100%. It will never go back. It will always just do the acid thing, which is donating a proton. So if you have a weak acid, what does that look like? We get a double arrow, meaning that we're going to go back and forth. So my weak acid actually stays together. So see how I have this hydrofluoric acid hanging out here? And look at in my solution how many molecules of hydrofluoric acid I still have. I still have lots of molecules of hydrofluoric acid. Actually, I have more together than came apart. So we say partial ionization. And so typically this is honestly about 5% for most weak acids versus 100% for strong acids and bases. So we indicate this with a double-sided arrow we're going to talk about a little later called equilibrium. That means that we can go forward and backwards. So a strong acid will do the acid thing and break apart, but whatever broke apart is also going to come back together. And so we have this kind of back and forth because it's not strong. The reason it's not strong is because its conjugate base is not very stable. It doesn't like to be in this form. It actually likes to have the hydrogen attached to it. So the stability of your conjugate base is going to be determine your weak acid like strength. The more stable your conjugate acid or your conjugate bases, the stronger your acid's going to be because it can exist in this form a little easier. If it's very weak, very unstable over here, it's not going to exist in that form. So it's going to go back and really hang out a lot in this form here. So a weak acid does not dissociate completely. It does not ionize completely. So it will be a weak electrolyte because it makes some ions, but it doesn't make a lot of ions. And so we'll say it only makes a light bulb glow dimly. It's going to be a weak electrolyte. Here are some weak acids. Remember though, if it's not strong, it's weak. You don't have to memorize these. You can just get familiar with them if you want to, but you don't have to. So what would the hydronium, remember hydronium is equal to H plus concentration be for each of these things. So I'm going to give you a little tip. This is the concentration of A. So we put this in brackets to indicate the molarity, the concentration of a thing. And so we can say determine the, instead of saying right H hydronium concentration, we can say determine H3O plus in brackets. That means the same thing as the concentration. So if I'm looking at this, I see 1.5 molar HCl. So pause really quick and go through these and see what you get, and then unpause it. Alright, so if you have 1.5 molar HCl, how many H's are in HCl? Well, there's 1. So it's a 1-to-1 mole ratio. So that's going to be 1.5 molar of your hydronium. Remember, hydronium is equal to H plus. So you can kind of just count your H's and say that it's a 1-to-1 ratio or 1-to-2 ratio. Now, these H's are not acidic. Only this one H is acidic for acetic acid. Now, this one is not a strong acid, right? So the HCl is strong, so it's going to dissociate completely. So this one is not strong. So are we going to make more, less, or equal to 3 mole? it's going to be a little less because it's weak. So you can say the concentration of hydronium is a little less than 3.0. And you'll learn later how to get the exact number for this, but we're just going to say it's a little less because it's weak. Okay, because weak. What about nitric? Is it strong or weak? Strong. So we can just say, hey, it's going to be a 1-to-1 ratio here. This is going to be the same concentration as the acid. Right? Okay. So if it's strong, you can just assume to use a mole ratio. If it's weak, though, it's going to be a little less than you think it might be if it were strong. So figure out what it would be strong, and then you can just say less than or dial it back. If you have a multiple choice question, you can kind of eliminate from there. Strong bases. So strong bases do the same thing. They break apart 100%. And so what I want you to notice here about your list of strong bases is that they are any hydroxide that's soluble. And so you don't really have to memorize a list. You just need to use your solubility chart. If the hydroxide is soluble, it's a strong base. It's going to break apart 100%. Weak bases, again, just like weak acids, are going to go backwards and forwards. They're not going to break apart as much. Notice that the ammonia kind of hangs out together. It doesn't really make a lot of ions. And so you do need to know a couple of weak bases. So here are some of these reactions. You need to know ammonia is a weak base, and I would know bicarbonate is a weak base. For Chem 11, you may be asked to kind of memorize some of these others, but for now, know that ammonia is a weak base and bicarbonate is a weak base. Otherwise, if it's not hydroxide and soluble, and I'm telling you it's a base, you have to assume that it is weak. So let's look at this. So we're going to determine the concentration of OH. So here, if it's strong, again, we can treat it differently than if it's weak. So go ahead and pause and find these out. So potassium hydroxide is strong. So it's going to be equal, right? I see a 1-to-1 ratio here. So it's going to be 2.25 molar is equal to our OH concentration. This guy is not one of my strong ones, so it must be weak. So I can say it's going to be less than. So OH concentration is going to be less than 0.35 molar here. And I can look back at these reactions if I want to see the mole ratio for these, but every one of these just makes one hydroxide. Then this guy, this is a strong, but look, there's 2 hydroxides for each one of these. So I have to multiply this by 2 because of that mole ratio. And so I'm going to have my hydroxide concentration that's equal to 0.050 molar. Okay. So water is special because it can act as an acid or as a base. So with itself, it will actually do this thing. When it's with an acid, it'll act as a base. We've seen that. When it's with a base, it'll act as an acid. It kind of is going to please whoever it's with. It will react with itself. So it will self-ionize. What does that look like? I have water hanging out with water in equilibrium with, so this is a weak behavior, creating hydronium, which is like an acid thing, and creating hydroxide, which is a base thing. So water can act as both. And actually does it 10 to the negative 14 is how well it goes in this direction, so not very much. We do get a really cool equation out of this, though. The equation that we get out of this is going to help us with these next problems. The equation is 1 times 10 to the negative 14 is equal to the concentration of hydronium times the concentration of hydroxide. If it's neutral, then both of them are 10 to the negative 7. If it's not neutral, though, you can use this. They always have to add back up to this constant. So this is a constant. Don't worry about sig figs with it either. So let's do some math with it. So pause and see if you can figure it out. You're going to use this equation. So 1.0 times 10 to the negative 14 equals the hydronium concentration times the hydroxide concentration. So pause, Plug these in, see what you get. Okay, so here are your answers. How do I get these? So I'm going to rearrange. I'm solving for OH. Take my equation up here and rearrange. So OH is going to be equal to the water dissociation constant divided by the hydronium concentration. Make sure that you're putting everything in parentheses in your calculator, and it shouldn't really steer you wrong. So when we're talking about acidity, you may think of pH. And so when we're looking at hydronium concentration, as I get a higher concentration, remember negative exponents give me bigger numbers, so higher concentrations over here, I become more acidic. Lower concentrations, I become more basic. For hydroxide, the higher concentrations are basic and lower concentrations are acidic. So pH is actually the a negative log of the hydronium concentration. So a low pH is very acidic. pH scale actually goes from 0 all the way to 14. A high pH is strongly basic. So you can think of water being neutral as at 7. So above 7 is basic, and below 7 is acidic. pH scale, and we'll talk about the calculations in a second, but the pH scale is logarithmic, so that means that it's 10 times more concentrated the lower your pH. So if I have a pH of 2, that's actually 10 times more concentrated than a pH of 3. And so it's kind of like the Richter scale with earthquakes, right? Like a 3 scale earthquake is 10 times stronger than a 2. pH is the same thing because it's a logarithmic scale. Now, you don't need to know anything about logs. We're going to talk about it in a second. You just have to find the button on your calculator, so don't get upset about thinking about I have to do log math or anything. Just find the button on your calculator and follow the equations. So we're going to look at the pH calculation. So the equation here is the negative log of the hydronium. That's actually what P means. P stands for power of hydrogen, so power means negative log of. So you can find the POH, negative log of the OH, P of anything is negative log of that thing. So pH is the negative log of H. So go ahead and pause and plug in your calculator and see what you get. Okay, so here are the pHs we should get. pH does not have a unit. Sig figs. The number of sig figs in your concentration equals the number of digits after the decimal place for your pH. So I'll write that down for you. The number of sig figs in concentration equals the number of digits after decimal in your pH or your POH or whatever you're talking about. Okay, so it's not just a regular sig fig rule, it's a little bit different. So if I look here, I have 2 sig figs total, 2 digits after the decimal place. All right, and so please let me know if you need help putting this in your calculator, but it's just a plug it in kind of thing. So what if I need to go backwards? What if I need to find the hydronium concentration but I give you the pH? So we're going to do the opposite. So to get out of a log, we have to raise everything to base 10. So again, we're going to just plug this into the calculator, pause, and see what you get. So here's what I get. I just plugged that into my calculator. And notice my sig figs, 2 digits after the decimal here, 2 total sig figs here. And so the same thing's going to happen with POH and pH. So a couple more equations that I can make sure. Yeah, a couple more equations I'm going to show you right here before we end. So the pH is equal to the negative log of H. So POH will be equal to the negative log of what? Well, of OH. That's what P means, negative log. So then to get out of this, the OH concentration is going to be equal to 10 to the negative POH. So you have to be careful, because if I give you hydroxide concentration and ask you for pH, you can't plug it into here and get the pH directly. Now there's another equation that we get from the KW, remember that water dissociation constant? If we take the pK of that W, we get 14. So, and if we do the P of the concentrations of OH and of hydroxide, we get the pH and the POH, right? So 14 is equal to pH plus pOH. This is a great way for us to kind of move through that. And then again, the opposite of this is pH equals negative log of hydronium. You have this way to get out of it, and then I'm going to repeat this water dissociation equation here, just so you have every equation on one page. Make sure you know what's on your equation sheet for the final and what's not on your equation sheet, so you need to make sure that you memorize the rest of them, because you need all of these that are on this page currently to do all your pH calculations. So the last thing we're going to talk about really quick is buffers. So buffers have to have two things. So the job of a buffer is to resist changes in pH. So our blood is a buffer. We have to make sure our blood does not get too acidic. That's called acidosis. It cannot get too basic either. That would be bad. So our buffers have to stay, our blood has to stay right around pH of 7.35 is what our blood needs to stay at. And so our blood contains carbonic acid. So it contains this carbon dioxide dissolved buffer system. So what a buffer does is it contains a weak acid and its conjugate base. So if you're going to make a buffer, you have to have two ingredients. You have to have a solution of a weak acid, and you have to have a solution of the conjugate base that goes with that weak acid. So what that's going to look like, so for example, so for example, a weak acid that I might want to use or talk about that's really helpful is acetic acid. So if we have acetic acid, what would the conjugate base be? So to get an acid to turn into its conjugate base, let the acid do its thing. What's the job of an acid? The job of an acid is to donate H+. So let's subtract the H+ from the acetic acid. So we get C2H3O2 minus the H, right? And then we have to subtract the plus, so we get a negative. What is this? This is acetate. So I can't just go to the shelf and find acetate. I have to find something with acetate, because we can't just have a negative. Where does it get the negative from? Because it's bonded with something that gives it an electron. So anything that's going to make acetate soluble is fine for me to use as a conjugate base. So acetate is always soluble, so it actually doesn't matter what metal I put this with. So I can choose sodium acetate. I can choose potassium acetate. I can choose ammonium acetate. I can choose any acetate that has what I need. What I want to make sure I do, though, is that I look at my moles of acid. I want that to equal my moles of acetate. So you want to kind of make sure you're choosing molarities and moles that are the same, because you want a good 50-50 mix of the moles in there. So how do they resist changes in pH? We're going to go way deeper into this when we get to equilibrium. It's so much easier to understand, but I'm just going to tell you now so you kind of have an idea of how this thing works. So you have two parts in a buffer. You've got the acid part and you've got the conjugate base part. So if I were to introduce a base into acetic acid, into the buffer, the acetic acid is going to neutralize this base, right? Making sodium acetate, making more conjugate base. If I add acid to the buffer system, then my base, my conjugate base, is going to neutralize the acid, and look what I make. I make more acetic acid. So I'm kind of going back and forth here with this conjugate base and this weak acid. If you add a base, the weak acid part of the buffer neutralizes the base. If you add an acid, the conjugate base part of the buffer neutralizes the acid. So it's got both parts. It's got an acid and it's got a base that kind of act with each other to neutralize any oncoming acid or base. So it's kind of like a system that really keeps your pH from moving up and down. We'll talk more about how this system works when we get into equilibrium. And then here's an image of what's kind of happening to this buffer system. You have the acid being neutralized by the conjugate base. You have sodium is kind of chilling as just a spectator down here. If you add hydroxide, your weak acid is going to neutralize that hydroxide, right? And so that's essentially what a buffer is. So if you've got questions about this chapter, please let me know. But go ahead and try to work through the homework using those pH equations and identifying buffers, and let me know how I can help. Thanks.